Hola, buenos días a todos.
Hello, good morning, good afternoon to you all, and thank you very much for taking part in this webinar. My name is Luis Cotanda, Director Marketing Manager of Agrovin. This webinar will take around 1 hour and a half. If during the webinar you need any support, you have any questions, you can use the chat box or use the questions and answers option in the platform. First of all, I would like to explain why or how we achieved the knowledge in order to offer this webinar. Well, we started in 1996 to build equipment of micro-oxygenation. And when we saw that this equipment did not comply with requirements from the caves and customers, we decided in 2007 to start to develop our own equipment. Nowadays, the Dosy-Ox equipment is able to independently treat different outputs with remote control. Many years ago, in 2007, we started working on the membrane contactor technology to be able to add or remove gases from the wine. In 2009, we already had a machine in operation on gas management before bottling, and in 2021 we work with the oxy-out, able to regulate content of dissolved gases in wine to flows up to 100,000 liters per hour. This last development helped us to understand the different applications, and then we saw that dissolved oxygen was not that important parameter in order to see the oxidation state of a wine. And that is why we started to develop or to study the impact of Redox Potential. In 2014, we started the first premises for the monitoring of ORP, but not until 2016 we were able to release electro wine to the market. After these many years, we have been able to work on the last model, not just able to monitor the ORP, but also to work on it. And all this experience enabled us to achieve a set of knowledge which we will be presenting today. This presentation will be given by Rebeca Lapuente. Ms. Lapuente is a part of the technical department in Agrovin, and she is our veteran in the control of ORP. And she works very closely with many other customers using the technology, not just in Spain, but also in the USA, New Zealand, and other countries. She is a bachelor in chemistry, and I would like to give her the floor. Good afternoon. Good afternoon, and welcome to this webinar. Good morning to those of you who are joining from different time zones. First of all, I'd like to thank you for your participation. Thank you for the interest you have shown. We know there are many, many people behind the scenes and also in front of the screen, because you are very interested in knowing more about Redox Potential, and that encourages us to keep on studying ORP and being able to share experiences. We decided to name this potential this presentation, Redox Potential from the paper to the cave, because we want to take the Redox Potential to your daily work in winemaking. A few years ago, when we started interesting in measuring ORP, when I was talking to one of my colleagues, he said, you need to explain this Redox Potential thing in a plain way, because my chemistry in high school was rather difficult for me. So the same feeling that this colleague had, we used this input, and we have heard more or less the same opinion from many of you, because you see the Redox Potential as a very far away concept from high school chemistry, and more or less you were seeing electrons moving around in the wine. So our goal with this PPT is you don't see this as a chemistry parameter, but as a tool enabling you to improve winemaking processes. To measure redox potential, we know it's a very useful tool and is really helpful in many processes, and it's really easy. You just have to think of it as when you think of measuring pH. You never think of protons or chemical concept, but you think that that is a parameter that is helpful in the winemaking processes that you need to know in order to improve the quality of your wines. So this is more or less the same idea behind this PPT. The redox potential is a parameter helping you to improve your wines from the point of view of oxidation and reduction. This PPT has two goals. The first one is to share more knowledge and that you get to know more about it. For us, it's a passion. It's a very interesting parameter, and we want to share our passion with you. And secondly, we want to talk about wines and winemaking processes and steps where the redox potential can be useful when managing the different treatments. We organized this PPT in 4 sections. The first one will be dedicated to knowing what is this concept and how it has a role in the industry in general, then in enology and or winemaking. In the third place, we will talk about what we really wanted to talk about, that is real cases and steps during winemaking where measuring redox potential can be useful. And then we will be showing experiments and real situations. So at the end, we will be able to compare two types of winemaking. One, or those where the ORP measuring has had a consequence or an impact on the final wine. Many times when talking about ORP measurement, sounds like something like very innovative, something new that has never been used, something that is absolutely new within the industry, the wine industry and industry in general. But we need to keep in mind that this is very well established in many industries, food industries. Many food industries use the ORP measurement in order to define the processes in order to get a high quality product. Industries such as meat industry, dairy products industry, they include this concept in their work protocols with ranges enable them to establish different quality ranges or see the need to implement a specific process to achieve an optimal quality. When we work on the ORP measurement, and when we need to work within certain parameters, we need to have an ability to modify these values in order to get values that are more in line with the quality we want to achieve. In the food industry, there are physical processes, such as the void packaging, that reduces oxygen content, that has an impact on the redox, on the ORP content, and also chemical processes called redox stabilizers, which are ingredients in the daily life products that we use or consume. These are the E for stabilizers that we find in the products that we consume every day. Among these ingredients used in food industry, there are compounds enabling the increase of ORP, like oxidant agents, enabling us to reach the values that we want to reach, and also other compounds enabling a reduction of the ORP through the reduction of the value of this electrochemical value, such as a compound that is very used in our industry is the E300, that's the ascorbic acid. Apart from food industries, where specifically when talking about a fermentated process, it is very interesting, such as the dairy products industry, where we see an anaerobic situation, so there it has no sense to measure oxygen. Apart from these industries where the redox potential is very interesting to measure, there are other industries, such as the water industry, where they use very much this concept in order to achieve certain values. In 1971, the WHO established this ORP potential as a reliable parameter to determine purification of water after treatment of 30 minutes, 650 millivolts. That gave the industry a water with enough quality to be consumed. We insist very much in measuring the ORP. Is a very used parameter, is very familiar in the industries, and it is essential to achieve the quality that we want to achieve. Now, within the enology industry, we are used to seeing, we're used to reading inside the properties of the enological elements, the different qualities connected to ORP potential. We are used to seeing that the application of certain product can have an impact on the ORP in wines, can stabilize the capability of buffering by the wine, can return redox status to the wine. But when we read about these features linked to a certain quality of the product that we can incorporate into the wine, what we are feeling is like the message is sort of empty, because we don't really know where does this come from and where this is going to lead us to. An advantage with ORP is that this is a parameter that can be measured. And when we measure it, we will get a lot of information when deciding about different treatments. Knowing about redox potential, when we introduce it to you, Many times you tell us that you just measure dissolved oxygen. I have a control of my wines, of the oxidation of my wines through the dissolved oxygen, and for you that's enough in order to see if the wines are in jeopardy or not. But now I'd like to show you the evolution of dissolved oxygen in the conservation of wine. We know that sometimes we will have higher values and lower values. Just imagine we want to measure dissolved wine right now, here. After racking, a week after racking, and we have a value of 0.3 ppi. Now we think that the level of dissolved oxygen is quite good, but if we see where we are coming from, we see that we came from a value that was much higher at the time of racking. We reached a content of 4.5 ppms that we didn't measure, that we didn't know about, and that oxygen has been consumed by our wines or in our wines until it reached the 0.3 ppm value. During the consumption of that oxygen, what happened is that many compounds oxidized. Oxygen has affected polyphenol compounds, and when we saw these 0.3 ppm, we never took into account that oxidation had already taken place. If instead of measuring dissolved oxygen, we measure redox potential, we would have, or we will be seeing a sort of all the accumulation of the oxidation. That is, we will be able to see with a higher certainty the risk of that wine, oxidation risk of the wine, and what is the evolution of the wine later on. Now, right now, that is what we offer you. We offer you the possibility to know the state of oxidation or reduction, the risk of your wines through measuring. We carried out an important work. We have been working on ORP for a long time, as Luis just told you. We have been thinking of it, monitoring ORP. We've been acquiring knowledge on a daily basis almost, and we are acquiring a lot of experience, working a lot on laboratories, in monitorization or monitoring in caves and follow-ups. And that way we are achieving a lot of experience, and we are in a way enabling you to know the values of the redox potential of your wines through our portable equipment, ElectroWine, and also through our fixed systems as another tool within Ulysses system. Okay, let's jump into what really matters for us, what really makes you really enjoy, that is experiences, real experiences about winemaking and fermentation processes and conservation processes. When we make a wine, many times we give a lot of importance to aging, and we need to take into account that from the time when the grape is collected to the moment when the wine reaches a home, a household. Let's think of a crianza wine, a red wine. There are many different steps. Many times you insist a lot on the type of cork, or how you are going to stabilize the wine, how much dissolved oxygen you will have at the conservation time. But actually, we all know that the most important time in winemaking, where the wine is really made, is the alcoholic fermentation. That is when a microbiological activity is really important, with the development of microorganisms with enzymatic activities that will give place to a certain structure, a certain smell of wine, a certain set of sensations of the wine. So would you say that right now we have enough information during alcoholic fermentation? If we think of it, right now, we work the same way as dozens of years ago. We measure density, temperature, which indeed are parameters that do not give us information. They just enable us to know that we are not having an issue. We are not facing a stop in fermentation. However, we forget that we could have a lot more information. We could have an outlook on fermentation, on what is really happening during alcoholic fermentation, and we could have a picture of the state of oxidation reduction of our must through the ORP measurement. When we measure ORP during alcoholic fermentation, we will witness a decrease in potential in this ORP. Development of microbiological and yeasts organisms will have an impact on ORP, on the redox potential. Starting from 200 or 300 millivolts, when talking about musts, with a lot of oxidative or oxidable compounds. These values decrease, and we could see negative values around minus 250 millivolts. And that's when fermentation is compromised, because yeast production is compromised. And this will be influenced by kinetics, variety, and type of winemaking. And that is a key moment that we need to start monitoring. When we monitor ORP potential during alcoholic fermentation, there are certain values that will give us information about potential issues or problems. So let's have a look at some of these values. Around minus 70 millivolts, that is when there is an increase in the risk of reduction appearance. And we know that around that value, there is a higher likelihood of sulfhydric or hydrogen sulfide. Below minus 250 millivolts, fermentation is compromised, as said before, because viability of yeasts is compromised under these ORP. During alcoholic fermentation, we already have values that we know that are risk values that we need to control and to see what are our tools in order to control them. Another piece of information of ORP measurement during alcoholic fermentation is that since we know that the tendency is to decrease if we add oxygen, whether it's micro-oxygenation or macro-oxygenation, if we see that the curve changes, that will be showing us that the oxygen input is too high, and then we have to reduce the dose or stop the treatment. Okay, let's see experiences and real cases where we changed protocols, and we have monitored the redox potential, and we have witnessed different values and modification, and we have been able to take some conclusions. Let's start with the effect of nutrition, the importance of working on organic nutrition since the very beginning of fermentation. Due to aroma reasons or lower risk of nitrogenated resources depletion, but also because that can help us control redox potential. We compared two different winemakings with two different nutrition. The first was 100% organic through our nutrition Actimax Natura, and compared to 100% inorganic with ammonium salts. When we used organic nutrition, values were higher, range of potential was higher too, and that had a consequence on the wine that allowed us to get a more varietal wine with more intense blackberries or black fruits. We were working on a Cabernet Sauvignon. In the case of 100% inorganic nutrition, we saw that redox potential reduced considerably. During alcoholic fermentation, there was a curve, a more steeper curve, and even though we didn't reach the minus 70 millivolts, the wine was not that aromatic. There is always a sort of hint of reduction notes, and we were reaching this risk of reduction. Other experiences that we wanted to show and share with you is the relationship between oxygen input and how this can have an advantage, and how redox potential can help us to establish a correct dose of micro-oxygenation. We will be showing you different experiences. This was a Macabeo winemaking. Enologies detected reduction notes in tank, reaching very low values, around minus 90 millivolts. And that let him know that there was a reduction risk. So he saw that in the tank and started micro-oxidation at a density of 0.1010 grams per milliliter. And that's how these reduction aromas disappeared. This was particularly interesting when we have Ulysses systems with a number of tanks monitorized that we, from our own laboratory or from the screen where we can see all the tanks, are able to have information, a very real information, that the tank is having a problem and that we need to start a treatment to remove this reduction risk. Here we can see a couple of experiences in two Californian caves, both using Ulysses. They were using compressed air racking, and they were monitoring redox potential and the reduction in density. We see that we used a very similar methods with 20 millimeters per liter per day. And we saw in these cases that even though we used these high doses of oxygen, we didn't have any problem of oxidation. On the contrary, we were working with very low redox values. We need to keep in mind that an oxidation itself is not produced by oxygen input, but by the value of redox where we are working. In this case, values were very different because they were different varieties, different winemaking processes. In a case with Pinot Noir, which is more mild, it's milder from the point of view of polyphenols, but Cabernet Sauvignon values reached were much lower, around minus 125, even working with oxygen input. Here we have three winemaking processes that are very similar, more or less twins, where we were working with the Ulysses system, with racking with compressed air, applying oxygen, same protocol of winemaking, macro oxygenation, and we were working in the three cases with Tempranillo variety. The fact that we were monitoring reduction oxidation potential enabled us to see that one of the tendencies of this potential, there was an increase of ORP, and that meant that the addition of oxygen included in our protocol in the three winemaking processes, in this case, was too high. So imagine what would have happened if we wouldn't have stopped the treatment, if we didn't had any clue about the redox potential. In this case, we would have faced a serious problem of oxidation because we would have been applying the protocol that we were used to. And this wine is much more sensitive to oxygen effect without the capacity to modify these values. When we measure redox, you might have seen that, and I remind you that we were using the Ulysses system, we want certain peaks, certain increases in potential in ORP, and these are related or are connected to the different compressed air injections. And many times you wonder why or if these injections have an impact on wine. And we see that even if there is an increase in the ORP, values are recovered immediately, and the tendency, the trend keeps being downwards. And this doesn't show there is oxidation. This means there is no contact between the probe and the liquid. And this means there is a decarbonization of wine, but no oxidation whatsoever. So we need to keep in mind the trend. We should be more worried about a change in the trend, that the trend is upwards instead of downwards. So in order to summarize, when we monitorize ORP during AF, we will be witnessing a reduction in potential. We will be working from higher values that in the case of the mass would be around 200 or 300, that will be reduced when we use certain products against oxidation, such as the typical combination of ascorbic metallisulfate, sulfite, and ethanine. But that does not remove oxygen, but that helps us reduce the ORP. During fermentation, this potential will be reduced. We will be reaching minimum values. And we need to try to avoid values below minus 70. Those are values that show a risk of reduction. Of course, we will always have to avoid reaching under 200 minus 200 millivolts, because that would mean stopping fermentation. And when we witness a change in the curve, a change in the trend in the ORP values, and we are working with oxygen input, we need to monitorize the dose, because sometimes we need to stop treatment, because when there is this change in the trend, that means there is a higher risk of oxidation. The fact that we control this curve, we have seen how it helps us when we are using oxygen. Also helpful is the use of organic nutrition from the very beginning. That is key to avoid brusque reductions of the ORP. In the case of organic nutrition is not among our options. Inorganic options should never be applied at the beginning, but always after exponential phase. And another tool to avoid brusque reductions of potential is to have a retarded start of addition of oxygen, because we know that oxygen is an activator of cell multiplication. So we will try to start adding oxygen 24 hours, 48 hours after yeast formation. The fact that we work using protocols, taking into account everything that has been mentioned before, should also make us think, or we should also take into account that there are other factors affecting ORP, such as turbidity, MOX, antioxidants. Everything is going to have an impact on minimum values of the potential redox potential measurements. The fact that we have botrytis, that is something else. Working with very low values of ORP protects us from chemical oxidation, but not enzymatic oxidation, that is botrytis. That should be treated in a different way. But also taking into account that variety and type of winemaking is going to have an influence in the minimal values reached of ORP. That's why it is important to measure in our conditions exactly how we work. We need to measure this ORP potential. So let's keep on moving forward. We will see an effect in the malolactic fermentation when we add oxygen. Many times you fear, or often you fear, the oxygen input during malolactic fermentation, but you need to remember that when we monitorize redox values and the values are very low, oxidation addition should not be worrisome. It is something that is going to stabilize the color of the wine during malolactic fermentation and to have more aromatic wines. In this case, we started monitoring redox potential when malolactic fermentation had already started, and they started adding oxygen at a dose of 3 milliliters per liter per day during 2 hours, and then a second treatment of 1 milliliter per liter per day during 1 hour to increase or enhance potential redox. We wanted to reach minus 30 millivolts in order to avoid reduction risks. And thanks to this, we reached a safety range, and then we started the treatment of maintenance at a dose of 3 milliliters liter month. Oxygen input was stopped. Then, and we saw that the wine, the resulting wine, had an aromatic profile which was much more open, more fruity than in the cases that when oxygen had not been added. And we also see the color was not or maintained much better, and the volatile variation had been more or less insignificant. Let's see now the impact of ORP during conservation of wine and how the different types of measurements in which situations will have an effect on the values, and how this shall also be taken into account when we reproduce our environments. In this first case, we measure ORP at different heights in the same tank in order to see how this height, this difference had an impact on on the measurement. And we saw that actually in areas that were higher in the tank, closer to the air, ORP potential was higher, whereas in lower areas closer to the lees, the values were lower accordingly. This is just an idea that where we put the probe is also important in order to be able to reproduce certain measurement from one year to the next. The fact that we measure ORP on wine aged on lees is something we haven't done yet. We know the effect on wine, we know the advantages at the level of a better organoleptic, a bunch of characteristics, better taste. But we also know that leaves have an antioxidant effect because they consume oxygen, but they're able to transfer compounds such as glutathione, which it has a very important antioxidant ability. So measuring ORP during the aging of wines on lees is also important in order to manage sulfur in a very key way. It is also possible that we might not need very high doses of sulfur, which is something that you always need to focus on. Another effect is it comes from the type of material, the porosity to oxygen from the different types of materials. In this particular case, we monitorize the same wine in two different sorts of container. The first was with permeability, a lower permeability to oxygen, and the second one with a higher permeability to oxygen. And we saw that in the case of lower permeability, wine was at lower values of potential, redox potential, than the other one, which showed higher levels of transfer of oxygen. Another aspect that interested us was to monitorize the effect of micro-oxygenation on the final wine. We saw how oxidation input during fermentation is very interesting. We can add high quantities without a big effect, but during conservation, values must be much more controlled and more linked to the qualities of the final wines, the desired final wines. And we wanted to study the effect of a low dose of oxygen, 1 milliliter month, on a wine that was structured Tinta de Toro, 70 IPPs. And we saw that this very low dose had a big impact. We went from minus 70 millivolts to 40 millivolts, which is more or less okay. But this gave us an idea that dose that we could add could have a very, very serious impact on the wine. To monitorize redox can be really interesting. Many times, treatments with oxygen are applied to final wines in order to polymerize tannins in too astringent wines, or in order to open wines that aromatically are a bit reduced. So the fact that we correctly adjust the dose is very important for oxidation of wine, and to monitorize ORP really helps us to know whether the dose is correct or not. Before bottling, we also wanted to monitorize wines. We wanted to see the effect of inert gases and to inertize wine with argon. We saw that argon allowed us to reduce ORP in wines, and this made us think how much the sulfide management is correct when we apply the protocols without knowing what is the ORP before bottling. Many times we work the same way before bottling and after bottling. Many times our customers use the same values throughout and then bottling, regardless of what we did before. But many times we see that in the market there are still wines that at the time of their consumption are oxidized or reduced. We are aware that around 50% of wines where there is a defect, that defect is connected to processes of oxidation and reduction. So I believe that knowing redox potential is really important, and from then on to correct sulfide in a more efficient way and more connected to risk of oxidation or not of that wine. Now, in order to end this first part, I wanted to share a study that we are now working on, where we wanted to see the evolution of redox potential in a bottled wine. As I said, there are wines that are oxidized or reduced when they reach the market, because when we start from a certain value, we'll have an effect. Also, there is an effect coming from the choice of cork. I just wanted to show you just, this is our first control. And we try to measure redox in wines after a month of bottling. And we see how permeability or resistance from the cork after just 1 month will have an effect on the ORP potential. In order to end my presentation, we are going to compare two profiles, two different types of winemaking. We wanted to design two different protocols with Sauvignon Blanc. The first protocol would be reductive and compare it with a traditional one. We wanted to be working on ranges of ORP ranges that were lower and monitorized redox in order to see that the protocol was reductive, in fact, and see what the effect was on the wine. We wanted to see aroma effect, but we also saw effects or impact on the conservation. In order to prepare this protocol, we started knowing that we will be watching an evolution, that we will be seeing low values, that we will be during fermentation and higher values during conservation with higher risks of oxidation. And our goal was to have a wine with aromatic persistence and to reduce sulfide. So we wanted to lessen the risk values using organic nutrition, enabling us to reduce the risk of a brusque reduction of the potential of the ORP, and also using sequestrants of oxidation precursors, reducing the risk, and also add glutathione with an antioxidation effect so that the wine was protected from the aroma point of view. In order to understand these results, I just wanted to clarify, to explain the reaction, the chemical reaction. When an oxidation takes place, we many times think of oxidation by the polyphenols and how quinones are created that have an impact on the aroma property and on the color of the wine. However, many times we forget that the second part of the reaction, as a consequence of the formation of quinones, also acetaldehyde is formed by the oxidation of ethanol. When we want to work on ethanol, of the SO2, Many times we need to control the control of acetaldehyde. Around 70 or 80% of acetaldehyde of the SO2 combined in the musts is combined with acetaldehyde, around 70 or 80%. So when we reduce the content of acetaldehyde, would allow us to use SO2 in a more efficient way. How this can be done? We will be working on oxidation precursors, as we said, with PVI and PVP. And we will inactivate quinones thanks to affinity with glutathione. Knowing this, we created two protocols, the control protocol, the traditional one with SO2 reception and organic nutrient, and an addition of SO2 at the end of alcoholic fermentation. The reductive protocol was different in the sense that we had inertized the tank during filling with carbonic snow. We used superbouquet evolution during decoupling. Superbouquet evolution allowed us that, allowed an antioxidant situation. And during fermentation, we used organic nutrition, Actimax Natura, which reduced the risk of oxidation by reducing the content of oxidation precursors and reducing the metals content, and also increasing content of glutathione during fermentation. After fermentation, alcoholic fermentation, we corrected SO2 content and an addition of superbouquet evolution to be able to conserve wine. If we see these graphs of evolution of both winemaking processes, we see that the green line, the reductive protocol, developed at lower values than the traditional control protocol. In the case of the reductive protocol, we saw minus 50 millivolts values. And in the control treatment, we were seeing 100 millivolts. What was the effect of this on the wine? When we saw the wines, we saw the control protocol had a smell of more mature fruit as compared to a more fresh fruit, with a feeling of higher acidity, even though they had the same acidity values. Both protocols gave a correct wine. The fact that both protocols gave a correct wine made some enologists think that, well, they prefer the protocol, the control protocol profile, smell profile, whereas others preferred the reduced protocol wines. So we were able to create two types of wine, just modifying the protocol and ensuring that through monitoring ORP, we were working on different potential ranges. However, the more interesting data came up when we compared the evolution of the wines. Those two wines were bottled and we analyzed 4 months afterwards. And we saw that after 4 months of bottling, reductive protocol wines showed half acetaldehyde than control, and that allowed us to work with 20 ppm less of SO2. And this means that we were able to reduce acetaldehyde content from 31 milligrams in control to 15 milligrams. So we were able, or we reduced 25% of addition of SO2 to reach the same SO2, free SO2 values, and to reach the same parameters of evaluation of oxidation, and seeing the different features. Working with 20 ppm less and to reduce the SO2 content in the wine didn't have any impact on the oxidated effect. Oxidated compounds were similar. Coloring or color intensity were more or less the same, was more or less the same. And also oxidation precursors were at lower values in the reductive protocol. So we expect that the evolution of this wine is going to be better if we work in a more efficient way on the SO2 addition treatments. How have we been able to obtain these results where we were able to work with a 25% less of total SO2? Well, thanks to two tools. The first is redox monitorization, which enabled us to know that we were really carrying out two different protocols. And the second tool is the addition of superbouquet evolution. It is an alternative to SO2 against oxidation, and it allows us to work with less oxidation risk, and it is developed within the Vinoso project, which goal was to use to have wines with less SO2. So in this case, we have been able to reduce by 25% the SO2 content in wine with two applications of superbouquet evolution in two different times in the elaboration, the winemaking process at dose of 20 milligrams. In order to finish, to end my presentation, let's have a look at the conclusions and a summary. We are aware these are a lot of concepts and we really want you to understand them and to see redox potential as something very useful to you. When we talk about redox potential, we are talking about very low values, and these very low values of potential show a reduction risk. So knowing and monitoring redox potential allows us to assess this reduction in oxidation risks. Risk of oxidation is increased when reaching values below -70 millivolts. That means these are values that we need to avoid. There is a real risk of fermentation stop when working below -250 millivolts because yeast production is compromised. In the case of oxidation risk, in values over 150, we will be risking aromatic oxidation, such as thiols, that we know they have a very important influence in the aroma compound of the wine, and over 250 millivolts show or lead to a very high risk of oxidation of wines. And when we want to have a reductive protocol, in order to protect aromas, to reduce the SO2 content, we need to work on very low values of redox potential, around -50 millivolts. If we have very low values, because we are working on a variety with high content in IPTs, and a protocol with a high transaction, we want to increase the potential and we need to manage oxygen. So we need to apply oxygen using the Oxidox systems and equipments that enable us to adjust the correct dose to adapt adapted to the type of wine and the winemaking processes. And in the cases with very high values of redox potential and we want them to be reduced, we need to use antioxidant agents. We just mentioned superbutane evolution as an alternative against SO2 oxidation and increasing the glutathione content, which is a natural antioxidant, and also adding tannins with high antioxidant compounds such as tannicol 1. And we know for certain that many or that their application reduce redox potential. So that means it protects against oxidation. And always we need to keep in mind that when we want to reduce or to work with the low values of SO2 at an industrial scale, we need to reduce redox potential, and only in those cases we will be able to assess SO2 inputs and we will be able to reduce its content before bottling. We already saw how measuring redox potential is helpful. What decisions can we make from the measurement of redox potential? Well, logically, we will have a reliable tool in order to know the status of oxidation and reduction. Without it, we wouldn't be able to know the risk of our wines of oxidation or reduction. We will be also able to better adjust the MOX dosage when they are necessary and when not, and we will be more efficiently using oxygen. This tandem oxidox electro wine is a perfect tandem, perfect combination for good management of oxygen input at any point of winemaking, and to adjust a dosage to that particular type of wine and that particular winemaking. And naturally, we wouldn't be able to know how a winemaking is going if we do not measure redox potential. We might think we are working on a reductive winemaking process when the case is not that. So we might be missing our goals because the range of reduction or oxidation are not correct. But we need to keep in mind that there are many factors influencing the measurement of redox potential. We need to know that measure in order to assess how we are working. We know that every wine is a complete different universe and every cave is different, and we encourage you to measure redox potential and that you are aware of the values and how you can improve your wines by modifying these values. Well, this is the end of my presentation, but before starting the Q&A time, I just wanted to thank two enologists that have been working with us for a long time. I would like to say thank you to Marcia Torres. She's working on a very important Californian cave, and thanks to her, we have been able to learn a lot about ORP potential. She helped us a lot when monitoring and when having interesting experiences, and she encouraged us to keep on knowing about redox potential and keep on working on it. And I also wanted to say thank you to Roberto Martin, who is a passionate of redox potential now. Many experiences that we are having now are thanks to his collaboration, and I didn't want to end my presentation without mentioning them because they too are a part of our passion about potential, redox potential. Thank you.
Hola, Rebeca. A ver,
Hola, Luis.
segundo.
Hello, Rebecca. Hi, Luis. Thank you very much. Yes, many questions are coming our way. I just wanted to ask you some of them because, well, I need to translate them. Well, the first one is at what time of fermentation nutrient additions have been made? I mean, in that graph, when you compared inorganic and organic nutrition, in that case, the nutrient addition was done immediately after the yeast sowing. The measurements, additions were made one after the others because the values were really low. But the reduction of redox potential had to do with the moment of the sowing of, of seeding of the yeasts. A second question is it feasible to measure redox the same way as we do when we measure the temperature at fermentation? Yes, of course, the same way as we measure temperature during fermentation, we can do the same when we need to measure redox potential. Same as measure of potential, both are tools linked to our Ulysses system. When we work with the different options provided by Ulysses system, well, the Ulysses system is not just about rankings using air, but to know the whole process of winemaking. So we are able to know temperature, and the same way we can monitorize redox potential, and we have different places all over the world where we measure redox in a continuous way. Another question is, the fact that organic reduction reduces Sorry, we didn't get that question from the Spanish booth. Can you please repeat the question? It's a bit confusing. Yes. Is organic nutrition the one dealing to a lower redox? Is that not a contradiction with the removing of reduction aroma when reducing ammonia? Well, reduction in potential is not going to be as sharp as when we use inorganic nutrition. In the second case, inorganic nutrition multiplies, or in a more tumultuous way, the effects. When we add nitrogen during a fermentation and in part reduction aroma can be reduced, we need to take into account that reduction is not just due to low potential value, but due to a nitrogen deficit. The fact that we use organic nutrition is because we need to reduce the risk of reduction from all the points of view, from the point of view of the chemical point of view, because the reduction of potential would not be as sharp, but also from the metabolic point of view, because yeast will have enough nutrition and is not going to create hydrogen sulfide. Another question. Would you say it is more important redox potential or nitrogen values when talking about reduction of hydrogen sulfide? Well, I would say both things. We need to reach a balance so that we don't have hydrogen sulfide. We need to have a balance between nitrogen content, avoiding formation of hydrogen sulfide by the yeast, and the organic nitrogen input that should not derive or lead to a too fast multiplication. So as said, if we do not want to use organic nutrition, but we need a considerable oxygen input, we will be using ammonia salts if that is what should be done, even if it is not very desirable. But we will always do that after the exponential phase of yeasts, so that we will have enough nitrogen. So there is not a deficit, but we would not be promoting a cell multiplication leading to a sharp reduction of the potential. So we will have to focus on a balance. Are there values linked to the control of aerobic or anaerobic organisms? I mean, I don't know if I understood this correctly. Is there a certain redox where microorganisms are aerobic or anaerobian organisms are or evolve or progress? Well, we saw that yeasts have a resistance threshold of up to minus 250 millivolts. So yeasts are able to survive at higher values than minus 250. But when we talk about aerobic, such as bacteria, we will be talking about much higher ranges, around 180 millivolts. So yes, there are differences, significant differences. And the fact that we work on different ranges may lead to certain organisms surviving more than others. And here is a longer question. If I have a white wine and I correct with SO2 normal levels, I will be favoring reduction risks at the bottling phase? Yes, of course. This is clear. SO2 is a reduction agent, and when we use SO2, redox potential will be reduced. If we are at 30 millivolts and we apply SO2 to 35 ppms, we will be causing a reduction, an important reduction of ORP, and then in bottling, the values might be even lower. So it will have a reductive effect. So aromas, reduction notes or reduction aromas are a risk. This is important when we are working on SOT, because there's no sense that all the wines are treated the same way when not all the wines have the same risk of oxidation. But they are at a higher risk of reduction in some of the cases. Now there are two questions talking about more or less the same. With monitoring of redox, would you say that we would be able to effectively avoid oxidation and reduction problems during winemaking? And the second one is, do you think that ORP control might enable us to have wines without SO2? Of course, when we monitorize redox, we assess the risk of oxidation and reduction, and we have the tools to modify those values. And we need to take into account that we are at fermentation. The decreased trend is very strong. So to turn up this trend, we try to avoid sharp decreases. So we have the tools for that. We can work on redox with these tools, and we are able to reduce the risk of oxidation and reduction. And about SO2 at the time of bottling, as I said before, to measure redox potential before bottling should be a required parameter in order to correct SO2. It makes no sense that when talking about oxidation risk, we correct the wines the same way, because not all the wines suffer the same risk. And derived from this, using same protocols with very different wines, then we have as a result very oxidized or very reduced wines, and the quality of the product is lower. And that comes as a surprise to the enologist, because the values of reduction and oxidations were not the same. But if he or she had measured ORP before, talking about SO2 or another element like oxygen, we need to inerticize or apply a different gas to reduce. So for both wines, when those 30 ppms are too high a value are not needed, both and or to wines that might need an extra treatment apart from this 30 ppm of SO2. Now, two questions, but more or less the same question. Is it possible to measure ORP at the laboratory, or we need to measure it in the tank always? In the first case, how can we measure correctly ORP at the lab? When we monitorize ORP, ideally, we have to measure it in the tank. When we take a sample and we take it to the laboratory, there is already an oxygen dissolution. There is a change in the ORP potential, and the value is not going to be representative of what we have in the tank. So we need the most interesting, what we really find useful is to measure redox potential inside the tank. In the case that we want to take it to the laboratory, we would need to find a complex solution to avoid oxygen effect or loss. Well, it is much more complex than when we monitor inside the tank. It is a more simple work or task. Now, this is in Italian. Let's see if I can translate this correctly. Can we foresee production of more complex and durable wines when we control redox? Yes, of course. When we work on avoiding reduction risk, we would be able to create protocols, and we are also able to see that the evolution of the ORP potential, as we said before, the difference between knowing dissolved oxygen and monitoring redox potential. When we measure dissolved oxygen, we just have a value, but we never know what was there before. But if we measure redox during all the process, throughout the process, we will be able to get more durable wines that we know they haven't suffered previous oxidations and that they have a higher resistance ability. Now, about bottling, are there adequate ranges of values before bottling for red wines and white wines? Well, these values, well, that is the $1 million question. It is complicated. We need to be working on low values. We have seen that values above 100 millivolts would have an impact on the aromatic profile of wines, would reduce perception of aroma. So values, the lowest possible values around 50 millivolts or 0 millivolts or minus 50 millivolts have an impact. There are values that give us a lot of information, and corrections of SO2 should be done from them. If we have 200 millivolts, we need to correct, and that is a range that is possible to find during a winemaking, but that would be a wine that is not ready to be bottled. But at values of around 30 or 40 millivolts, that is a one that is more protected against oxidation. So that could be like an objective value. Are there mobile equipment to measure ORP that can be moved from tank to tank or not? Well, we have two different possibilities. One is fixed equipment, fixed facilities using Ulysses system. That is one option inside the Ulysses system. And we have the portable equipment. You mentioned it before during your presentation. And this equipment is a portable equipment. Depending on the model, it has different a number of probes. And of course, these can be moved from one tank to another. We also have the possibility to work together with the oxygen options, because some of these equipments also have the OCOX option. So it can be done through mobile or through fixed pieces of equipment. Okay. At a fermentation stop where there is no reduction aromas detected, can we think that this stop is not due to too low redox potential? Well, if there's been a stop in fermentation and there are no reduction aromas, it is complicated, but it is not impossible. We need to take into account that hydrogen sulfide during fermentation, when we talk about low values around minus 70 millivolts, is formed through the elemental sulfur coming from the field in the must. If we do not have a high content of elemental sulfur, if content is too low, we will be able to reach very low redox potential values during fermentation without formation of hydrogen sulfide, because chemically there is not a possibility. However, we might be reaching very low potential values, leading to stop in fermentation because values are too low and yeast is not able to survive at those very low values of potential. When we work at in a massive manner, adding ammonia, a big amount of ammonium salts may lead to stopping fermentation due to a brusque, sharp reduction of values of potential. And that means that it's very, very difficult to reverse that, because the trend is very descendant, very downwards. And we need to foresee that in order to avoid the stop in fermentation. And the last one, I think the last two questions, if I have recently made wine and we add sulfide for its conservation, how can I regulate this potential to avoid that? How can I, if I have a very low redox and I add SO2, what should I do in order to maintain redox at a very low values without adding SO2? Well, if I have a low redox values, I might be thinking about reducing reducing SO2 inputs. Or ask myself, why am I using it as an antioxidant protection? Maybe I do not use that, or I don't need such a high dosage. In the case of needing to increase redox potential during conservation because there are reduction aromas, we might add oxygen in a controlled manner to keep the potential balanced values. Always keeping in mind that the SO2 added in a big part is going to be combined due to the increase of the redox potential. So the important thing here is, do I really need SO2? Can I use a lower dosage that would enable us to have wines at an acceptable levels of SO2, and we would be able to control the potential increase after adding SO2. So the key question is, do we need SO2 or maybe a lower dosage? And the last one, what is the impact of temperature, fermentation temperature, in the decrease of redox potential? I mean, how much does temperature of fermentation impact on reduction potential? Well, it has an impact. The higher the temperature and the faster the kinetics, the sharper the reduction, because temperature ranges are not always used the same way. If we need to ferment because our profile of wine requires fermentation at 26 degrees, okay, we should be fermenting at those temperatures. So we need to work the reduction of potential from a different pathways, such as not adding yeasts, etc. But if we ferment at lower temperatures, multiplication is going to be slower and kinetics is going to be slower. So the reduction of potential is not going to be as sharp. Okay, thank you very much, Rebecca. Those of you who asked questions that had not been solved because we do not have time, do not worry. We will be answering them using the email. I just wanted to say thank you, Rebecca, and thank you, Vinide and InfoWine, for helping us promoting and supporting the webinar. And from my part, this was all. Thank you so much. And see you soon. Thank you very much. Thank you.